Good morning to all. In today's test session, I am going to cover a nonlinear method, basically pushover analysis and time history analysis, and pushover and time history analysis. So here, both pushover and time history analysis are nonlinearities. Mean by nonlinearity, seismic nonlinearity, and how to assign the nonlinearity into the various elements. Then what is the moment rotation relationship is there. So that first of all introduction we will see, and then next is a time history analysis. In that, incremental dynamic analysis is one of the recent method is there to estimate the seismic capacity of the building. So that also introduction. So whatever the 2 hours are the our session is there, I will split into two. First, I will cover in the first hour. I try to cover the theoretical background of this particular and nonlinear methods. First, we'll see and discuss, and then we'll go into the SAP how to perform these, how to assign the nonlinearity in the SAP 2000, and how to perform pushover and time history analysis, and what is the this incremental dynamic analysis. Plus, in the yesterday's session, there was some doubts regarding the soil structure interaction, how to model that. So that also part we'll discuss in short in today's session. Okay. Now, before to start the the nonlinear analysis, in the last lecture we have covered about we have discussed about the different seismic nonlinear methods. So we know that this particular chart is there. So this particular chart is the complete description about the seismic nonlinear methods. So basically it is a static method and dynamic method is there. In the static method, it is linear method and non-linear method is there. So this linear method, in that equivalent static load method comes, this is IS code based method is there. And this is the non-linear method. So in this, the static non-linear is the pushover method. So today we're going to discuss this particular in detail about the pushover. And this is a non-linear method. And next is dynamic method. Dynamic method, again, the linear method and non-linear method. So in this, so a linear method is a response vector method, is the IS code 1893. In that this particular method is there. And next is the non-linear method is the time history analysis method. And in detail, if we continue the time history analysis, then it is a incremental dynamic analysis. Then for the structure, actually, which method is appropriate, whether to go for a static method or whether to go for a dynamic method. So dynamic method is the most realistic. Dynamic method is the most realistic method. So in the dynamic method, actually, to the structure, we are applying the dynamic load. So we are applying dynamic load. So this case is realistic to a earthquake case. In the earthquake also, we are applying the dynamic load on the structure, and we are getting the we are getting the dynamic response of the structure. So therefore, this particular method is the most accurate one. And but it is a time consuming method is also. It is a rigorous method. So therefore, you require a latest software, and your proficiency should be there in that particular method. Not dynamic method is there. As far as the response spectrum is concerned and time history analysis method. So these are, hello. Sorry. नहीं होगा ऐसे बोलते ऐसा नहीं चलेगा, करना ही पड़ेगा मैनेजमेंट। Okay. Just I will repeat this. I forgot to share the screen. So it is so today we're talking about the non-linear different methods are there, static and dynamic. So the question is that, so which method is preferred for the seismic analysis? So it is so preferably go for the dynamic analysis, because dynamic analysis is the realistic methods are there. In this, it is a modal combination rule. It is a modal combination rule. So in the dynamic analysis, especially nonlinear time history analysis and response spectrum analysis, it estimates the response in every mode, each mode, first mode, second mode, third mode, and then combined by using a modal combination rule. So therefore, it is the most realistic. While as the static method is there, so in that the equivalent static method, and it may be pushover analysis method. So in this, these two methods preferably be applicable if the structure is the first mode dominated structure. First mode dominated structures are there. So what is meant by first mode dominated structure? The mode in which the mass participation and the in the first mode is more than 90%, then that is a first mode down. So that is possible only if the structure is symmetric in plan as well as in structural point of view. Then pushover or equivalent static load method is applicable. Then, so after mist analysis, if we extend this, then this comes the incremental dynamic analysis. Okay, so we'll discuss about this particular method also. Okay. Then very quickly we'll see the each method. Equivalent static load method. So in this, the basic assumption is that the structure is idealized as a single degree of freedom system. Actually, multi-storied building is not a single degree freedom system, but we are, for the sake of simplicity, we are assuming in this particular method as it is a SDOF system. Okay, SDOF system, and then so if it is single degree of freedom system, then response in the first mode is we are assuming to be a predominant. That is, mass participation is in the first mode is more than 90%. Then this particular method is applicable. Okay, so in this, what we are doing actually, the earthquake induced forces, we are converting into equivalent static loads. Earthquake induced forces we are converting into equivalent static force, and this force we are applied at the different floor levels. We are applying at the different floor levels at one time, only at one time. And after application, what are the response in the structure? That is, what are the shear force, bending moment is there, drift displacements are there. That is, we are estimating. So that is, this is whole of the calculation is based on one equation, that is VB, base shear. So we are calculating base shear, and that base, according to that base shear value, we are distributing. That is equivalent static load method. Then this is a response spectrum method. So response spectrum method is a dynamic method. It is also included in IS 1893. So it is a dynamic method. So it is a dynamic method in this sense, it estimates the response in each mode, first mode, second mode, third mode, up to how many number of modes the software or manually it is required to consider. So that is up to which the mass participation becomes to more than 90-95%. Then those many number of modes are required to consider, and then afterwards these are combined by using a modal combination rule. So in the IS 1893, two methods are there, modal combination rules are there. First is CQC method and SQRSS, square root sum of square method is there. So by using either of this method, if the two modes are close to each other, go for SRSS, or if it is widely spaced, then go for CQC. Okay. This is a third method, which is a static method, but it is a non-linear. Static method, but it is a non-linear. So this is also, in this case, the structure is pushed on one side. Okay, but the force, it is pushed in a steps. Gradually it is pushed, and we get a curve, what is called as a capacity curve. Okay, so there is a lot of use of this particular capacity curve. So this gives the seismic response of the building right from initial up to the final. Similarly, so pushover curve is a response curve. Pushover curve is the response curve. So similarly, we know the method, that is the tension test on a mild steel. So we apply the force initially and gradually goes on increasing. Okay, goes on increasing up to the failure. Then the material undergoes various states. First is there is elastic range, then proportional limit is the first, elastic upper yield point, then highest ultimate point, then breaking point. In this case also, whenever the structure is pushed by applying a gradual load, it is pushed by applying a gradual load, and until failure. So therefore the building, different elements undergoes a different states. Okay, different states where it is yielding. Then after the yielding, how much is the inelastic displacement is there? How much is the inelastic displacement? So that information we will get from this. Okay, so that is a pushover method. In detail, we'll discuss afterwards about this pushover method. Okay. Then lastly, this is a time history analysis method. It is most correct and most rigorous because if the building is of unusual configuration is there, in which the mass participation definitely in the first mode will not be more than 90%. Torsion is there, dominant torsion is there, or there is a coupled behavior between the translation and torsion is there. So in that case, we have to obtain the seismic response, we have to go for a time history analysis. So time history analysis is based on one basic equilibrium equation. So that is inertial force is there, inertial force plus damping force plus this is a stiffness force is there, and then it is a ground motion component is acceleration component is there. Okay, so this equilibrium equation is there. So this is, in this case, the structure is subjected to earthquake excitation, which is a realistic case, we say, and we obtain the building response. So this is a building response, and this is a ground motion response. Ground motion. So we, and then what is the acceleration? What is the acceleration, velocity, displacement in the structure that we are getting? This is the output from the output of this particular analysis. So this is a nonlinear dynamic analysis. So out of these four, two methods are linear methods and two methods are non-linear. So what are two methods linear? In this, the material is assumed to be elastic in nature and the structure is idealized as a single degree of freedom system. And two methods are non-linear and time history method, in which the structure is it is required to analyze by using a non-linear procedure. This is about a methods of analysis. Okay. Then to deal with a nonlinear method, we must know what is a seismic, what is meant by a nonlinearity, what are the different kinds of the nonlinearity, how to define this nonlinearity to the particular element or the structure. Also required to know this. So basically, the nonlinearity, the kinds of non point of view. So it is a first it is called as a material nonlinear, and next is called as a geometric nonlinear. Then the question is that whether both nonlinearity is required to define or required to assign, that is material nonlinearity as well as nonlinearity. The answer is yes, because this nonlinearity is different and geometric nonlinearity is different. So it is required to apply the both nonlinearity. Okay. Sometimes if the geometric nonlinearity in this is nothing but P delta effect. So if the P delta effect is not a dominant, if the P delta effect is a not that much dominant, but it is required to check initially. Okay, so then if you neglect the geometric nonlinearity, then well and good. It analysis, but on the material nonlinearity, yes, definitely it is required to define first of all. Just 1 minute. Then material nonlinearity, what is meant by material nonlinearity? The relation between the material stress and stress is a nonlinear. So across the cross section of the element beam and column, the relation between stress and strain, if it is a nonlinear, it is a nonlinear. So that is a material nonlinearity. Then how to assign this particular nonlinearity to the element, that is a column or beam? Then, so there are two approaches are there. Either we can assign this nonlinearity, material nonlinearity, either by using this particular approach. This is called as a lumped plasticity approach, or we can assign by using a distributed plasticity approach. So both approaches are correct on this thing. So this is most simplest one. That is lumped plasticity is most simplest one, and this is a distributed. What is the difference between this and this is that in the case of lumped plasticity approach, we are assigning the nonlinearity to a specific zone of the element. For example, the nonlinear to the beam, nonlinear to the beam. How to apply this? Okay, nonlinearity to the beam. How to apply this? So in this case, the nonlinearity to the beam is applied to the specific zone only, not to the complete length of the beam. So that is for the column also. whatever the length of the column is there, the nonlinearity is applied to a specific zone where the element is likely to be fell under the earthquake. So that is a lumped plasticity approach. And in the case of distributed plasticity, the nonlinearity is applied for the complete element, for the complete length of the beam, for the complete length of the column. This. So especially if the shear walls are there, shear wall is also a lateral load resisting important element is there. Shear wall, it is a shell element completeness. So how to assign the non-linearity to the shear walls by using this approach or this approach? Then both is possible. To the shear wall, both is possible. The lumped plasticity approach also, by this particular approach also we can assign the non-linearity, and by using this approach, this is also. But in the case of shear wall, this is most appropriate. Okay, because this non-linearity is applied to the complete area of that particular shear wall. So this is about the material non-linearity. Then in the case of geometric non-linearity, what we mean by geometric non-linearity, it is the strain and displacement is a non-linear. The relation between the strain and the displacement is a non-linear. So what is known as a P delta effect. So you might have read this particular term. So that is, this particular term is applicable only when the structure is subjected to the lateral force. So it is a P delta effect. So what is a P delta effect? Okay, before that, now where to assign the non-linearity, which are to which element, especially for the buildings. So in the building, different element components are there. Important joint is also there. Then slab is also, yes, shear wall is also a lateral load resisting element. Shear wall is also there. Brick masonry, lateral forces. Then the non-linearity to the brick masonry infill is also required to assign. So this is about this. Then foundation, that this part is something different. Then non-linearity we have to assign to each and every element. If the non-linearity is not assigned, which non-linearity? Material non-linearity is not assigned, and if the pushover analysis is performed, what will happen? We have not defined the non-linearity. So therefore, the pushover curve, we will get the pushover curve as a straight line, linear. We'll get a pushover curve as a linear, right? So that is so because we have not assigned the non-linearities, then where to yield, after the yield, how to behave this, that what is a backbone curve, we have not defined. So therefore, essentially, whenever to go for a nonlinear analysis, before to that, it is very essential that we have to define and assign the nonlinearity. Then to define the nonlinearity, we must know under lateral load how that particular component will going to behave, how this particular component will fails. For example, under lateral load, how its behavior under gravity load we know, but under lateral load, how the beam will fail. Obviously, the beam will fail under flexure as well as it fails in shear. Where it fails? At which section? Okay, so under lateral load, if you plot the bending moment diagram, a frame subjected to lateral load, so bending moment diagram, it is triangle. Here it will be maximum and here it maximum. So therefore, maximum compressive, maximum flexural stresses and maximum shear stresses will be the end zone only. So end zones are vary. These are the probable locations. Therefore, we have to assign the non-linearity on the end zones only, for especially the beam. Okay, so what kind of non-linearity to the beam? Yes, flexural non-linearity as well as shear non-linearity is required to assign. Okay, then what is about the column? What is about the column? How the column fails under lateral loading? So the column fails again flexure, but it is a coupled action. So it is a flexure plus axial. Okay, so the column fails under axial plus flexure coupled action, or it may fail in shear. Okay, so here also where the column fails, so column fails in what is the probable location? Probable location is again at the ends. At the ends it fails. So here also for the column also non-linearity is required to define at the ends only. Then what is about the joint? How the joint fails under the earthquake loading? So joint fails under shear only. The joint fails under shear only. So therefore shear kind of non-linearity is required to assign to the joints. Okay, so this is about the basic elements, what is called the primary elements. Similarly, what is about slab? So we are modeling slab as a shell element and we are assigning a diaphragm constraint. So we are assuming that the slab is behaving as a rigid diaphragm. So therefore, there is one constraint in SAP 2000. So it is required to assign that particular diaphragm constraint to that particular. So then next is what is about a P delta? This is the lateral force because of the seismic. Okay, now the column will move from this to this. The column will move from this to this. So deviation is how much? It is equals to delta. It is equals to delta. Then at the base, what is the moment? At the base, what is the moment? So it will be equals to ph into h. That is because of the lateral loads. This is the moment in a clockwise direction. And because of this now, this is gravity load into delta is the additional moment. What is called as a P delta moment. Okay, it is called as a P delta moment, and what is called as a P delta effect is called as a P delta effect. Now this particular P delta effect is very significant if the gravity load the column is heavily subjected to axial load. Okay, so in that case we should have to consider P delta on the column. So what will happen now? Because of the lateral force, the column gets buckled. The column gets buckled, and it is subjected to action. So there is a column becomes that particular column becomes more flexible, soften. So therefore, because of the P delta, there is a softening behavior and due to that, the stiffness of the lateral stiffness of this particular reduces. So this is the effect. So therefore, the P delta effect is also significant if the loading and whenever this column is subjected to heavy load. So this is about the P delta. Okay, and then I will go for the third presentation. Now we'll discuss about the pushover method, pushover analysis method. Okay. Now this is a detailed methods of analysis. The pushover analysis method is here. Pushover analysis method is here. So it is a static type, static nonlinear method is there, and it is a this one. Now pushover method, after pushing the structure to calculate the inelastic displacements, after yielding whatever the displacements are there, we are calling that displacement as the inelastic displacement. To calculate those displacement, there are two methods are there. First is called as a capacity spectrum method, and number two is called as a displacement coefficient method. Capacity spectrum method, this is developed by ATC40. Document is there in 1996, and displacement coefficient method is there in detail in FEMA 356 2000. Okay, displacement coefficient. So both methods are there to estimate the pushover. Only performing pushover is not sufficient. After getting the pushover curve, that is not sufficient. To calculate the inelastic displacement, we have to go either for this method or this method. And third method is there, what is called as a modal pushover analysis. What is third method? So this is developed by Anil Chopra, and it is proposed in 2002. Okay, modal pushover. There is one limitation of pushover method. What is that limitation? Pushover method is applicable only for first mode dominated structure. So go for a pushover method. Okay, but if the structure is not first mode dominated structure, if it is not a first mode dominated structure, that is in which first mode mass participation is not more than 90%, then whether not to perform pushover analysis method, but as per the modal pushover analysis method, which is proposed by Anil Chopra, so here we can perform the models. So in modal pushover analysis method, the response in the higher modes are also considered, and then it is combined by using modal combination rule. So that is a modal pusher. But again, there is a limitation. So the modal pusher analysis accounts the response in the higher modes, no doubt. But there should not be torsion. Torsional stiff building should be there. Torsional mode is not acceptable. Okay, so again, this method is there, but limitation now with respect to the torsional response. Okay. Then, what is use of pushover curve or pushover analysis? Okay, so it is nonlinear static method. So it estimates the seismic capacity, seismic response, right from initial state to final, how the particular building behaves Okay, so that this thing, it is very simple to perform. It is very simple to perform. If the pushover analysis is performed for old building, then it is easily we can identify which are the weaker elements are there. So when we the pushover analysis starts, okay, so those elements which are weaker, which are element, so those elements will fail first. So hinges will be formed in the those elements first. Okay, gradually increasing of the load, gradually increasing of the lateral load, what happen further, another elements, okay, which are stronger than the first one, weaker one. So those elements which, so what is the sequence of the failure, which is the sequence of the failure, so that we can be identified by using a pushover analysis method. Okay, so this method is very useful for deciding the retrofitting strategy. Okay, so to decide the retrofitting strategy, there are two approaches: whether the retrofitting the building is require the retrofitting at the local level only or in the global level. So the local level means sometimes open parking story is there. Okay, so sometimes the failure, many failures in the open story we found. Okay, so in that case only the concrete jacketing of the open story column is more than sufficient. Okay, so that is called as a local this thing. And sometimes the building has a global this thing deficiency, that is its first mode is not a translation mode, it is a torsion mode. So then by providing the shear walls, we can change the mode, elastic mode, from torsion to translation. That is a, so shear wall is provided right from bottom up to the top. So therefore if this kind of strategy we have provided, then that is called strategy. So all this information, for this purpose we required a capacity code, what is called a pushover code. Okay, then in the pushover method the structure is pushed by applying a lateral forces. The structure is uh, pushed in one direction by applying a lateral forces. But what is the pattern of that lateral forces? What is the pattern of lateral forces? So lateral forces, so first of all it behaves up to this particular point, it behaves about the elastic nature, so therefore stiffness will be constant. After that there is a gradually the it is a bending, so it is a curve, so that is stiffness goes on reducing. Why the stiffness goes on reducing? Because after reading somewhere in this portion the element starts to crack, element starts to crack, and therefore because of the cracking what happened, the stiffness goes on reducing, and therefore this curve goes on this thing bending this thing. Then again there is a reduction in the this thing, reduction in the stiffness, again this reduction in this, so slope of this line gives the stiffness. So this thing, and afterwards this, so it is showing the maximum force here, and here there is a collapse. So this is a complete collapse or complete capacity is there. So from this where it is the yielding, then what is inelastic, importantly is what is inelastic displacement, that information will get from this. Inelastic deformation is nothing but after yielding from this, after this to this, after this point to this point, whatever this deformation is known as, this displacement is called as a inelastic displacement. What is the significance? What is the use of this inelastic displacement? What is the significance? What is the use of this? Inelastic displacements are the displacement which are there after yielding. The structure in which inelastic displacements are more, that structure we are calling as a more ductile. So in the case of earthquake resistant structures, the design for earthquake resistance is nothing but we have to just increase the performance in such a way that the inelastic displacement should be more. Inelastic displacement should be more, so that the structure becomes a more and more ductile. And actually we are not designing for ductility, so ductility is achieved in the structure by means of a whatever the provisions given in IS 13920. So that is ductility. By means of a reinforcement detailing we are achieving the ductility. Okay, now what are the different steps to perform a pushover? Okay, so first is first of all create a model. As usual, create a model, apply the load, whatever the different loads are there. Okay. So that is definition. Then after applying the load, then define the non-linear tube to different elements. Assign hinges. If the distributed plasticity is there, then define that particular non-linearity. Okay, so to each and every primary component, load carrying capacity, lateral load resisting elements, to that all those elements apply the non-linearity. Okay, then define the load cases. That is, define the load cases in the sense apply the loads on the model. Apply the loads on the model. Then gravity load. What are the different gravity loads are there? Dead load permanently is there. Then brick load is there. Then floor finish is there. Then this is fraction. This is indicating a fraction of live load is there. So whatever the loads are there which are remaining permanent, therefore it is called as a gravity load, which are remaining permanent load. Apply all those loads on this thing, and then calculate the calculation of the story masses. So in the software, automatically it calculates the story masses and then run the analysis. These are the simple steps are there. Okay. Then about the nonlinearity, just we have discussed about the nonlinearity. Okay. So the nonlinearity to this particular beam. So where in the building, this beam is somewhere here. Okay. So there are in the software SAP 2000, there are two approaches. There are two approaches to assign this particular nonlinearity. So in the figure, if the nonlinearity is applied in the specific zone here and here, so this is called as a lumped plasticity approach. So in this case, it is required to assign hinge here and assign hinge here. Now to assign the hinge, okay, how to assign hinge? Based on this, in the SAP 2000, there are two approaches. This particular hinge we can assign by using directly auto hinge. This auto hinge is there. Auto hinge minimizes the calculation. Many calculations are there. Okay, so it is required to do the calculation of moment. First is moment curvature calculation is there. First is moment curvature is there, and afterwards moment rotation is there. In the case of column, again there is a rigorous calculation is there. Okay, so we can assign this particular hinge by using a auto hinge procedure, or we can calculate all the properties. We can calculate all the properties and then assign the hinge. Okay, only thing is that it is a time consuming. If the conventional member is there, if the conventional member RC column beam is there, then go for auto hinge. It minimizes shape, and many researchers have worked that, and by using the auto hinge as well as by using a user defined hinge, the results are near out same. So for the conventional element, usually go for the auto hinge procedure. And if it is a non-conventional element is there, if it is a composite section is there, then that auto hinge is not available. So in that case, using a section designer command in the SAP 2000, you create a section, and then calculate the moment curvature, then moment rotation, define all these things, calculate all the properties, and then assign the hinge. Okay. Then next is after assigning the nonlinearity, this thing, then on a model apply the gravity load, and then apply the gravity load. Okay, apply the gravity load, and after applying the gravity load, so in the model, after apply the gravity load in the sense, you run the analysis. First of all, you run the gravity analysis, then pushover analysis. So what is the starting point for the pushover? What is the starting point for the pushover is at the end of gravity load case. At the end of gravity load case, whatever the stiffnesses are there, that is the initial stiffness for the pushover, and the pushover start from this. So don't forget that before the pushover, first of all run the gravity load case and then start the pushover. Okay, then see, then perform the pushover. In the case of pushover analysis, the load is applied gradually. So in this way, so first apply the load gradually. So we are here now. Then next, increase the load. Again, increase the load. Okay. Now this is a backbone curve. This is nothing but a backbone curve. For which element? This is backbone curve for this. Which curve it is? Moment versus curvature. This is a backbone curve. So this is already defined for this particular column, this is already defined. So therefore, this particular hinge and defined in the sense hinge has been assigned there. And after when the movement reaches to this particular, the hinge has to behave like this. So therefore, it is called as a backbone curve. Then if we increase again this thing, again the load, then the hinge will be reached to here. Okay, now there is a yielding. There is a yielding. Okay, again increase the load. Then now the hinges has been formed in the order. So what this indicate that among this, in this, whatever the different components is there, the hinge has been formed in this particular element first. So what we call this? This is a weaker element compared to the other. This is a weaker element compared to the other. Now the hinges has been formed in the other elements. Okay. Then next. Then if we increase, again the hinges have been formed. So this is progressive failure. It is showing the progressive failure. Again the deformation and displacement, roof displacement at the top is increasing, further loading. Okay, then further loading, and then see the hinge is changing the color in this column. So it is this shows a completely failure. This shows the completely failure. While as the colors in the other hinges, there are different colors are there. So for example, this particular hinge is here. Now this particular is here. That means this is just yielded. This is just yielded. Okay. Then after performing the push-on analysis, then to estimate the inelastic displacement. To perform the inelastic displacement, we required a method what is called as a capacity spectrum method. So this is performance estimation after that. So there are two methods to calculate the performance. One is a capacity spectrum method, and number two is the displacement coefficient method. So in the capacity spectrum method, which is developed by ATC40 in 1996. So in this, the two curves are superimposed. Which are those curves? First is this curve, what is called as a capacity spectrum curve. I am not saying as a capacity curve. Now it is capacity spectrum is there. Okay, and this is called as a demand spectrum. I am not saying it is a demand curve. It is a response spectrum, but it is called as a demand curve. So here, what is the axis? It is a spectral acceleration versus spectral displacement. Spectral acceleration versus spectral displacement. On these two axes, these two curves are superimposed. Then it is called as. Then after performing the pushover, analysis, okay, then this is our response spectrum. ISO 1893 response spectrum. What is called as a demand curve. It is called as a demand curve. So this demand curve is what is axis? It is spectral acceleration versus it is a period is there. So this is a demand curve is there. Now convert this curve into a demand spectrum. That is, you just convert the axis. Okay, now this is spectral acceleration. This is also spectral acceleration. But here this is a period. This is a period. This is a period is there, time period is there. It is converted into a spectral displacement. It is converted into a spectral displacement using this equation. Now this equation is this equation is called as this equation is applicable only for single degree of freedom system. Applicable only for single degree. So here the method is applicable only for here. There is one idealization is that the structure is idealized as single degree freedom system. Okay, so convert it into this by using. Okay, now next is building capacity curve. Now building capacity curve is also required to convert into a capacity spectrum. Okay, so this building capacity curve we get from pushover analysis. Okay, pushover analysis. So it is what is a curve? It is a base shear versus roof displacement. Base shear versus roof displacement. We get this capacity curve. Now this is converted into a capacity spectrum. So what is it in the case of capacity spectrum? This is base shear axis is converted into a spectral acceleration, and roof displacement is converted into a spectral displacement. Okay, spectral displacement. Nature of the curve will be same. So here also, for the conversion from base shear into spectral displacement of roof displacement into roof displacement into spectral displacement, we require the equations. So here, these are the equations. Again, these are equations are applicable for a single degree freedom system. So therefore, in the capacity spectrum method, there is an idealization that we have to assume the structure as a single degree freedom system. And then again, the capacity curve is there. Capacity curve is there. So that capacity curve, this is our capacity curve, is required to split into two two segments. What is called as a bilinear. आवाज थोड़ा कमी करो. बोलता थोड़ा डिस्टर्ब होता. Okay. This capacity curve is converted into a two segment, what is called as a bilinear representation. Okay, now the bilinear representation, again there is a method how to do the bilinear representation. Actually it is a what is called an iterative procedure is there, but in the software it is inbuilt, so not necessary to do the user need not necessary to do the calculation for this. So here, so this is a capacity curve and this is a bilinear curve is there, bilinear curve. So why it is required to do this? Because to calculate the effective damping. So that is damping up to yield point. It is the structure is remaining elastic. So 5% damping is there. But after yielding, the damping goes on increasing. Stiffness reduces, damping goes on increasing. Time period is also increasing. These are the changes in the properties of the basic structure. So therefore, to calculate the effective damping, this is the equation given in ATC40. So therefore, in this, these parameters are required. So that is a and K in this equation is called as a degradation factor, and that is to be taken from that particular table, FEMA 2003. Okay, and okay, so this is the table given in ATC40 regarding the degradation factor of K. Okay, then after doing the bilinear representation, then calculate the reduction, spectral reduction coefficient, SRA, and spectral reduction in acceleration and spectral reduction in velocity. Okay, and then after that, there is a reduction in the demand curve. Now, what is reduction? That is when we initially the structure has a capacity, lot of capacity, but after yielding, as I said that after yielding, the stiffness goes on reducing. Therefore, lateral load resisting capacity goes on reducing. Damping increases, time period also increases, and therefore the structure will not take the load, seismic load, as in the case of previous. So therefore, there is a reduction in the demand. So there is a reduction in the demand. So this is called as spectral reduction. So spectral reduction in the both sets, so acceleration also reduction and displacement also reduction is there. Okay, then next is that, then again, so this is the reducer and this is our capacity curve. So wherever there is an intersection, it is called as a performance point. Okay, so what is the outcome of capacity spectrum is that to know what is a performance point. To estimate a performance point, the capacity spectrum method is required to perform. Okay, so that is, so this is a performance point is this. So wherever the intersection of demand curve and capacity curve. Okay. Then next method is the displacement. Next method is the displacement coefficient method. So what is the outcome? What is the use of displacement coefficient method? To calculate the what is called a target displacement. So in the pushover, we are pushing the structure by applying lateral force, but up to what displacement? There should be some calculation. What is called as a target displacement. So to calculate the target displacement, this method is there, displacement coefficient method. So in this also there is a bilinear representation is there, but this the procedure for this bilinear representation and the previously in the capacity spectrum, this is different. So here in this case, this is a red line shows the bilinear representation. So this is this is passing from, so this is called as a shear, base shear at yield. And this point, this line should be passed from a point where it is, this is equal to 0.6, 60% of the base shear at yield. So this line should be passed in such a way that this point should be 0.6 of this total. So this is a bilinear representation in this case. While as in the capacity spectrum method, this area, whatever this area on the left side and on the right side, this area should be same. This is in this. Then, okay, as shown here. So this is the 0.6 of V1. Okay. Then by using this initial stiffness, and by using this elastic stiffness, these two stiffnesses are required, and this is for the further calculation. Therefore, a bilinear representation is required. Okay, so therefore, then by using initial stiffness and elastic stiffness, effective time period is calculated. Elastic fundamental time period is calculated, and then this is the equation to calculate the target displacement. C0, C1, C2, C3 is there. These are the coefficient modification factor to relate the spectral displacement C1, and this is to consider the C3s for the P delta effect. If you are considering the P delta effect, which is a second order effect is there, then this particular modification factor. Then the values of all these are given in FEMA 356. Okay. And again, this equation is applicable for a single degree freedom system. So therefore, here for this method is also there, is applicable for a first mode, that is a for SDF system, first mode dominant structures. Okay, so this is about a pushover method. So in the pushover method, for the capacity estimation, just remember what is the conclusion from this. For the capacity estimation, there are two methods in there: capacity spectrum and the capacity spectrum method and the displacement coefficient method. Capacity, why to perform capacity spectrum method is to estimate the performance point. Why to do the displacement coefficient method? To calculate the target displacement. Okay, this is my second presentation about the pushover. Okay. Then I will go for the third presentation, what is called the incremental dynamic analysis. Incremental dynamic analysis. It is a time history analysis. Okay, now time history analysis, as per as the seismic analysis point of view, this is most rigorous. So that is, from which method we get the correct and most realistic results? The answer is a time history analysis. Non-linear time history, because linear time history analysis is also there. Modal time history analysis, it is also called as a fast non-linear time history analysis. Am I audible? My presentation is clear? I'm not hearing anybody's voice. Am I audible? Is it clear? Yes, sir. Thank you. Then, most realistic result we get from the time history analysis. So to perform time history analysis, what we required? The ground motion. We required a ground motion record. So from where to take a ground motion record? Many sites are there. For example, for severe ground motion records, usually the researchers prefer the peer strong motion records are there. Pacific Earthquake Research Center is there at California. So many stringent earthquake records right from 1940 are available on that particular site. And in India also many research centers are there. IIT Roorkee also, they have own site and they have some records also. So from those stations we have to get a ground motion records to perform this. Okay. Now the time history analysis required because for this particular, because if the structure is regular in both sense, that is architecture point of view as well as structural point of view, then its performance, its modes are translationary, not a torsional. But this is rarely we find that if the photos show the multi-story building architecture point of view, there are many what we call the projections are there. Okay, and usually the architect goes for this particular kind of structures. Architecture beauty is the first priority. So if a tall buildings are there, then this structure becomes unusual. Its performance because unusual. So therefore, pushover analysis is not sufficient. Pushover analysis is not sufficient for this. Okay, if the structure is resting on a sloping ground, here also pushover analysis we can perform pushover analysis, no doubt about this, but the results are not that much realistic. So therefore, in this case, we have to compulsory go for a non-linear time history analysis. But to perform a non-linear time history analysis, it is most rigorous. And non-linearity, whatever we are talking, so then this non-linearity has to be assigned very clearly to each and every. That is, we must know, user must know what we have assigned that particular element. So without knowing, don't go for this particular analysis. Okay, then these structures are there. Some structures are of a special importance. Hospitals are there. Then nuclear power stations are there. So to estimate the seismic, to obtain the seismic response of this, we have to go for a rigorous time history analysis. Okay, so that is there. Then so to perform a this thing non-linear time history analysis, what is essential is that whatever the material is there, concrete, its hysteresis behavior, cyclic behavior, it must be known. Okay, because it is a we are performing a non-linear time history analysis. Time history in the sense ground motion we are actually applying on a structure, and so ground motion it is cyclic nature. So the material its cyclic behavior right from first to up to cyclic behavior, what is known as the hysteresis behavior. So that must be known. And additionally, that is about the structure point of view. Material hysteresis behavior must be known, and ground motion record is required, but how many record is required, that is also a debatable issue is there. So a set of ground motion records are required. We'll discuss about in detail. Okay, so therefore non-linear time history analysis is it is an again a regular what is called a conventional non-linear time history analysis one. And in depth, if we continue this thing, it is an incremental dynamic analysis, IDA, what is called as it. So what is output we get from a ground motion? We get the response to that particular ground motion, response of the structure to that ground motion. Response in the sense, what is the acceleration, velocity, displacement in the structure? What are the nodal displacements are there? Okay, nodal displacement, drift is there, displacements are there. All for a particular ground motion will get. Okay, and what is the difference between this and this? Incremental dynamic analysis, if from this we get a capacity curve, just like a pushover curve. So, but this curve we call as a dynamic capacity curve. Dynamic capacity curve is very important, and that we can obtain only by incremental dynamic analysis, not by conventional. But while performing this, okay, so incremental dynamic analysis, the procedure is same, just like while performing this thing. Only thing is that here some scaling is required. Okay, and this is required in a certain steps. Okay, so that we'll discuss this. So this is a nonlinear time history analysis, and this is the basic equation. The basic equation, and we are applying a ground motion, and we are getting the building response. Okay, so this curve and this whatever this behavior and this behavior is different. This is a building response is there. If we change this building, if this change the building, this behavior is different. Okay, right? So therefore, so it depends on the building properties. If it is a masonry building, the response will be different. Okay, this is called as the maximum response. In incremental dynamic analysis, we require the maximum response. Okay, not all responses. There are many peaks are there, but what is the maximum response that we require in the incremental dynamic analysis? So this is a excitation, that is a ground motion record. Here also there is a many peaks are there, many peaks are. Maximum peak, what we call as a PG, peak ground acceleration. Yes. So this is building, this is a ground motion response, and this is a building response is there. So in this case, first of all, create steps are the create a model, then apply non-linearity to each and everything, then select the ground motion records. So number of records are required, this thing, and then run the analysis. Then here, this is about we are talking about the incremental dynamic analysis. So from the, what is the outcome of incremental dynamic analysis is that we get a capacity curve, what is called as a dynamic pushover curve. Okay, so the capacity curve will be like this. So what, all these lines are wavy lines are there, and number of lines are there. So how many ground motions? So the incremental dynamic analysis is performed for number of ground motions, number of ground motions. For each ground motion, we get one curve. For each ground motion, we get one curve. So here, I think 8-9 lines are there. So that is, in this analysis, 9 ground motions are applied for the same structure. Okay, so that is called as an incremental analysis. Then question is that whether one curve is not sufficient. This is a capacity curve. It is a dynamic capacity curve. What information this particular curve gives? This one curve gives how the building behaves, or what is the building response, for a particular ground motion. For this ground motion, what is the response? Okay, it initially it behaves elastically, then there is a little bit hardened behavior, then it soften is there, and afterwards the curve is flatter. So it is supposed to be the building, there is a structure has been collapsed. When the curve becomes to horizontal, then stop idea analysis. Okay, so that is, so whether one curve is not sufficient? No, one curve is not sufficient, because how we can say that the building is safe? Building is safe by seeing the performance of only one ground motion. So all these records are past records. All the records are past record, and we know that any earthquake never repeats. The future earthquake, what will be its characteristics? What are the characteristics of that? It is not known, so we cannot predict. So therefore, the what is the concept behind is that you take a number of ground motions. Apply on a structure, and then you will get a number of curves, and the mean of this will be something. The median will give the median capacity curve with all this, which is the average absolute. So by taking how many number of ground motions, take as many number of ground motions, the capacity estimation, it will be more and more correct. So in this analysis, this particular curve is on y-axis and x-axis. On y-axis, just it is written the acceleration, it is a intensity measure. On y-axis, what to take? Okay, on y-axis, what to take? It is a intensity measure it to take, and on x-axis, it is building response. Okay, it is a building response. So here on y-axis, it is called as an intensity measure. Intensity measure is nothing but it is a ground motion related parameter. And this is building related parameter. It is called as an engineering demand parameter, or this is also called as a damage measures. Okay, so this is ground motion related parameter. What is called as an intensity measure is nothing but the parameter which defines the ground motion parameters, ground motion characteristics. So what are these different parameters are there? Well, first is the PGA is there, P ground acceleration. Then spectral acceleration, SNT1 is, we express the ground motion. So select any one from this. Okay, again there is a selection. Proper selection of intensity measure is also a part of research. It depends on what is your structure. Okay, so then and then only your response will be correct. For example, if your structure is a multi-story building, and if it is a first mode dominated structure, then usually select a SAT1, whatever this SAT1 as the ground motion measuring parameter. Okay, if it is a torsion dominated building is there, then usually select a PG is this for the as an intensity measure. So all this regarding the selection of intensity measure, that is given in Wamasco paper, Wamasco 2002 paper. So regarding select, and many research, you will find many research on this selection of intensity measure for IDA. Then this is building related parameter. So when the ground motion is applied, there is a drift and displacement is there. So how the response we are measuring the response. So response in terms of what? So response is measured in terms of global drift. Response may be measured in terms of interstory drift. Most of the code and researchers are recommending you select always for a interstory drift. Interstory drift is the building response parameter is there. So here building response parameter, and we'll get the then whatever the material is there, define the hysteretic behavior. Okay, so for example, RC building under cyclic loading, So many researchers have performed this thing study on this, and these are the hysteretic loop. Okay, the concrete is subjected to a cyclic loading. Then these are this thing. This is the behavior. Okay, so the behavior is there. Then many researchers like a Clog is there, Takeda is there, Susan is there, Neslan is there, and then Stone Taylor is there. All these are there. They have performed the test on a concrete under cyclic loading. They are testing and develop this particular model, what is called as hysteresis model. So different models are there. Some models are hysteresis models are we call as a stiffness degradation model for a concrete. Then strength pinching behavior. Whenever there is a significant reduction in the stiffness, then pinching behavior. These models are there. Okay, then the models are like this. These are different models are there. Okay, then these are the software. So here the user need not necessarily to worry about this particular behavior, because for example in SAP 2000 Takeda model is already inbuilt. Takeda model is already by default it is. Whenever we are performing a time history analysis, there is a default Takeda model is there. So it takes account of the cyclic behavior of the concrete. ETAB and SAP is one and same. OpenSea is another software is there. Okay, so in that also some inbuilt hysteresis models. Seismostruct is also there. If we go for Seismostruct is such a this thing software in which incremental analysis is inbuilt, just like a SAP 2000. Pushover analysis is inbuilt in the SAP library. Similarly, if you want to perform an incremental dynamic analysis, then go for this particular software, because there it is inbuilt. Then after getting a capacity curve, maybe from a pushover analysis or maybe from a incremental dynamic analysis, then define the damage state. Then what is the use of that capacity? So on this thing, capacity curve, define these particular stages. Okay, so this is slight damage, moderate damage, extensive damage, and complete damage is there. So define these particular stages. Okay, now how to define this? Again, the code have given many information. Slight damage, moderate damage, extensive damage, complete damage. What is mean by slight damage is description here, and this is in the ATC 40, ASC 41 is there, ATC 58 document is there. All these description about the damages are given. Okay, and actually in the code they are quantified also. For example, FEMA 356, this document is there. So in the FEMA 356, 3 damage states have been defined. One is immediate occupancy, life safety, and collapse prevention. These are the performance objectives. These are performance objectives in the performance-based design. Okay, so therefore, this is a when immediate occupancy, when the immediate occupancy has said to be occurs when interstory drift reaches to 1%. When interstory drift reaches to 2%, it is a life safety, or it is called as a moderate. And when it is a interstory, okay. Then regarding incremental dynamic analysis, regarding the selection of the ground motion. Okay, so then select how many. So again, there is as I said, there is a debate on selection of the ground motion, how many number of ground motions we select. So some this thing, FEMA P 695. Okay, so 2007, it says that you choose a 11 pairs, that is 22 ground motions you select, and preferably after selecting the ground motions, there it is required to scale. because if you plot the response spectrum of each ground motion, it shows a large variability. Then if such ground motions you apply as it is without scaling, then there will be a large variation in the capacity estimation. So there is a difficulty in prediction of the capacity of the structure. So therefore, all the ground motions are required to scale. Again, many researchers were worked on this. The Wamasco 2002 has given one simple step, what is called a one-step scale is there. And then next is a FEMA 356, FEMA P695. It is two-step scaling is there. So different codes are also there for scaling. Then in SAP 2000, the next is how it is performed. That actually I am demonstrating on this thing. So first of all, you choose the first ground motion, okay, and say reduce the amplitude of the ground motion to say 10% or 5%. Then apply on the structure and get the maximum response. Then you will get the first point. Okay, so after perform this, then once again you perform the time span analysis by increasing the amplitude. Initially, suppose it is 10% is applied, now increase to 20%. Then get the maximum response, so you will get the second point. Then again the amplitude, increase the amplitude. Once again perform the time span analysis, you will get the third one. Again increase this, then you will get the point like this. And this stage will come that all these points will be horizontal. Then stop incrementing. Okay, so this is said that stop incrementing when numerical non-convergence is occur. Okay, so then join by a line. So in Excel, this particular facility is there. It is to be again cubic SP line is there. Is there. So by that it just thing, and we get a. Okay. So we get a curve like this. So this is from one ground motion. Then you take the second ground motion. Again, reduce the amplitude to say 5%. Apply on a structure. Get the maximum, you will get the first point. Then increase the amplitude, and every time get the maximum response, you will get the another curve. Then third ground motion, and then number of ground motions. Then this is a multi-idea curves. You will get. Okay. After multi-idea curve, then find the mean of this. This is going gives the median capacity. So see, all the curves afterwards becomes a flatter. So it is said that the structure has been collapsed after this. And this is the median capacity. Whatever the green line you are seeing, this is called as a median capacity of this thing. And this is called a median curve, average curve, median capacity. By applying a 10-15 ground motions, then plot a median curve. This is called as a median ID curve. Okay, and this is median curve. This particular gives from this to this range. The behavior of the structure is said to be softened. That is a stiffness degradation is there. From this to this, it is a linear. Okay, the curve is behaving as a linear. After that, the element cracking is there. Then pseudo linear is there. Softening, instability. These are the different stages I have defined. Okay, so this is about the increment dynamic analysis. So this paper I am talking about the Wamasco. You go for this particular paper for a increment dynamic analysis in detail. Okay, so this is my second presentation. Okay, so then now I will go into the software. Response please, because I am not hearing anybody's sound. I'm not hearing anybody's sound. Shall I continue?
Yes,
Shall I continue, please?
Yes.
Yes. Okay, thank you. Okay, now I will go into the software. Okay, now already we have developed the model in day before this thing session. Then we'll perform the same pushover analysis and time history analysis on that particular model. This was the model. Okay. Let me tell that one point is that I have made certain changes in this, not dimension changes, but hurriedly we have prepared that this particular model hurriedly. I make the changes and made this particular building safer for the by response spectrum analysis. So what the changes I made in this, whatever the internal walls are there, its thickness is, I have applied an internal wall of a 150 mm, external wall of a 230 thick. Okay, so that particular load I have make a change in this. Then whatever the load we have applied at the top story on a peripheral beams, all those are removed and only a parapet load has been applied. Okay, which is it is a correct one. Then also the floor finish loads have been applied on the intermediate floors. Okay, and then on the top floor I have applied a waterproofing load. Okay, so all these loads, whatever the loads we have applied, so that we can see. See here. So live load is applied, then parapet load, internal wall, external wall, floor finish, and waterproofing. All these loads already are there, which is applied. Okay, that is one change is there. Second is that I made the changes that column orientation. Our column size previously it was a 300 by 500 something. So which were oriented along x direction. So I have changed the orientation along x direction to along y direction. The reason is that, simple reason is that along y direction span is more. It is a 5 meter is there. So therefore I thought that, and in along x direction is 4 meter. There is no significant difference in distance. But even though, since it is 5 meter, therefore I have changed it to in this direction. Now how it is changed? That shortly I will this thing, how to change the orientation. Okay, so this is a column. Okay, suppose you want to change the orientation of this, then select this particular column completely. Select this particular column completely. Okay, so then go here, assign frame and local axis. Assign frame, local axis, and just write here as a, now it is 0 degree. Now we are turning it to 90 degree. Okay, now it is turned to 90 degree. Okay, now I will again make it just like a previous. Select this, assign frame and local axis, this command. Now again it is to be 0 degree. Okay, and now it is turned. Okay, now it is turned to this thing. Now I will make similar to this. Okay, this is, so go here, assign frame, local axis, 0 degree, sorry, 90 degree. I have to change this 90 degree. Assign frame, local axis, 90 degree. Okay, so in this way I have made the changes of this. Okay, the next is, okay, next is the scale factor also have been changed. Which scale factor? Equivalent static, just I will show. Load case. Okay, now we have defined two load cases. Equivalent static load case we have defined along x direction and along y direction. That is as per ISO 1893 equivalence. So this is scale factor. This is modified. Previously it was kept as a 1. Now it is modified to 0.5. Why it is modified? Because the response spectrum given in ISO 1893, that is for MC level of earthquake. but we are not designing the building, any structure for MC earthquake. We are designing it is for dB level earthquake, and so therefore intensity, therefore in the equation it is Z by 2. To calculate AH, it is Z by 2 because we are converting intensity from MCA to dBA. So therefore it is to reduce from MCA level to dBA level. So 1 by 2, that is 0.5, it is made here. Then reduce DT, and then the building is designed. Some call there is a failures has been shown. Then the sections has been revised once again, and final sections I am getting as a beam section as a 230 by 300 is sufficient. Then column section is 300 by 750 because building is resting in severe seismic zone, 750 mm. Concrete is M25 and Fe 415. Okay, so that is the changes. Then in the dynamic analysis, we know that there is a diaphragm constraint is there. Diaphragm constraint. Our assumption is that the slab should be behave horizontally. It should be behave as a rigid diaphragm. So therefore, the command is there here. Which command? So go for XY plane. This is for XY plane. Okay. So we are at the top. We are at the top here. So select this. How to give a diaphragm command? I will explain. Select all. Then go for next. Select all. Then go for next. Select all the slabs. Then go for next. Okay. Now all the slabs have been selected. All the slabs. And go here. Assign joint, and constraint. Assign joint constraint. Okay. Then here there is a diaphragm. Here there is a diaphragm constraint. Diaphragm, add this constraint. Okay, so this is the name. So constraint in which direction? We are allowing the slab to move in X direction. We are allowing the slab to move in Y direction, but not in the Z direction. So constraint in Z direction and apply to all levels of the slab. So click here and then okay. Now this is green indicate that the constraint has been applied. Now slab has been it behaves as a rigid diaphragm. Okay. Okay. So this is the procedure for this. Then after performing the analysis, just we'll see a modal analysis. What are the changes in this? Okay. Then display deform shape, only a modal. Modal case, yes. How the building deforms? Somebody has in the previous session asked the question translation, rotation. What is either the mode? These are the modes. What kind of mode it is? Translational. It is not rotational. Okay, it is not torsional mode. Okay, now this is called as a torsional mode. Okay, now this is translation, but along Y direction. Next, this is again translational. Again this is rotational mode. Okay, now this is animated picture is there. Okay, if we see the plan of this. So this is in the first mode. It is pure torsion, pure translation mode. See, it is moving like this. It is pure translation. If you see the second, it is torsion mode. If you see third one in a Y direction, but it is a translational. Again, it is translational along X direction. Again, it is torsional. Okay, and all this information in the tabular form you will get only in the display. All the analysis results you will get in the display show table, and go here. It is a structure output. And only we require a modal information. Structure output, all the structure base reaction forces you will get here. modal information and select this. Okay, so modal load is there. This is the related with modal information. Say next is modal participation factor. This we require. So many times we talk the mass participation C. This is the first mode. This is the first mode. What is the time period? 1.01. What is the participation? What is this? Is 91. 90 has been translated, has been excited in the first mode. So therefore, the structure is first mode dominated structure along X direction. Okay. Then what is about second mode? Second mode, here it is mass participation 0. Here mass participation is 0. Okay, 0, 0. And but it is a torsional mode is there. It indicates it is torsional. Go forward mode. In X direction, no mass participation, but in Y direction, 83% is there. So what kind of this thing? It is a translation. Okay, so it is a translation mode, but this is the first mode in the Y direction. This is the first mode in the Y direction, because in the first mode, so this is the first mode. Okay, then fourth mode is this. Then next translation mode is this. Okay, now just I will note particular time period, because in the time history analysis we require this particular time period. Which time period? Okay, along X direction, just remember, along X direction, this is a translational mode is there. So time period is 1.07. 1.07 is the time period, and in X direction, next translation mode is this. Okay, fourth mode is what is time period? 0.32. 0.32. Okay, next along Y direction, this is the first one. What is time period? 0.79. And next translational mode. Translation, this is not translation, this is almost 0. Next translation is this. What is time period? Is 0.20. 20. This is required for the further in the time history analysis while defining the damping. Okay. Then next a modal participation factor is also there. Then modal frequency is also there. Further calculations. Okay. Okay. Now I will close this. Now we'll go for the pushover analysis and time history analysis. Now time is half an hour is there. Now first is, before to this thing, define first of all a gravity load case. Define a load case. Okay. Now in this, this thing, time history analysis or pushover analysis is to be performed after the gravity analysis. So here already I have defined this particular gravity analysis, gravity load case. So what is this gravity load case? Define this as a new load case. Just I will modify. I have given this as a gravity load case, and it is a static nonlinear. And these many gravity loads which are remaining permanent, which are always permanent on the structure, that is just added here. Dead load, external wall, floor finish, internal wall, live load is there of magnitude. Reduction is 0.5 parapet and this is just a create new load as a gravity load case. Okay. Then very quickly how to define a hinges to the beam and column. Okay, so just I will show as a representative, just I will show to the beam and columns how to assign the nonlinearity. So first of all, we'll assign the nonlinearity to the columns, to the beams. What kind of nonlinearity? Flexural nonlinearity. Then first of all, select the elements, select the beams. So select properties and friction and beam. All the beams have been selected. We can check in the 3D views. All the beams have been selected. So the element to which the nonlinearity is to be defined. Then go for assign frame, assigning the nonlinearity. So go for assign command, assign frame and hinges. Here there is facility of auto hinge. Auto hinge avoids the rigorous calculation, and the results are also near to same that of the user defined. Okay, now one add this, add this. Now this table comes. Now there is a rigorous calculation behind this. It is inbuilt, therefore we cannot see this calculation, and 356. Okay, so this is old version, 14 version. If you refer the 21 version of SAP 2000, then ASC 41 just revised in 2013. So the coefficient values are taken from ASC 41. So this is FEMA 356 2000 edition. Okay, then here it is a concrete beam. Select the member. If it is steel beam, steel beam. In this case, it is concrete beam. Okay, then define the degree of freedom of that particular hinge. So what is degree of freedom? M3. What is the beam? The beam is going to deform in this direction with respect to axis, local axis 3. Okay. Then while defining the hinge, okay, so it is asking, it requires one value, shear force value. Now the software is asking that from which load case the shear force is to be taken. So that is, it is to be taken from the gravity load case. So therefore gravity is already defined. So we are giving the information that take the shear force from the gravity load case. Okay. Then here it is, transverse reinforcement is confirmed if the given building, given structure, if it is a special moment resisting frame, then check this. If it is a old building is there, which is a poor in ductility, what is called as a simple moment resisting frame, then uncheck this. Now it is a special moment resisting frame, say okay. Okay. Then this is one hinge is assigned. Then similarly at the other end, it is 0.9, add this. Okay, same information comes. So this is at the other end of the beam. Other end of the beam. Okay, so now we have assigned to the beam, every beam, 2 hinges at 0.1, 0.9, and then say okay. See, hinges have been assigned. Hinges have been assigned to all the beams. To all the beams. Okay. So this is for the beams. Then we'll assign to the columns. So what is the required procedure is that first of all select all columns. So select properties, frame section, and column. Okay, all columns have been selected. All columns have been selected. Then the procedure is same. Go for assign frame hinges, assign frame hinges. Then here it is 0.1, 0.1, add. Now here it is make as a concrete column. Make as a concrete column. Okay, now degree of freedom. Now for the beam it is M3. For a column it is PM to M3 because there is a coupled action is there. Axial load plus this thing. So degree of freedom of that hinge will be this. Okay, then what is changed here? Take the shear force, required shear force for the calculation for the gravity case. Then yes, it is a ductile column and okay. Then this is at the one end. Then at the other end it is 0.9. Add this. Again same information comes. Okay, so at the both ends of the column we have defined. Okay, okay. Now this is we have assigned the nonlinearity to the columns also. Okay. Then this is a flexural nonlinearity we have assigned. We have not defined a shear hinges. There is one reason also to assign the nonlinearity to shear hinges. Why? This thing. So because this is a new building is there. This is a new building. New building is a special moment resisting frame. It is a special moment resisting frame, and it is a firm. We are very guaranteed that this building will never fail in shear. There is a confinement effect is there. So therefore, to the new building, it is not necessary to assign the shear hinges. Only if this particular element fails, different element fails, that fails only for the shear. Also, the nonlinearity whether to the joint is required to assign? No, because this is also a new building. We have just designed the building for a new building as a special moment resisting frame. Therefore, the joint is also not failed, will not fail for shear. So therefore, the shear type of a nonlinearity is not required to assign here. Okay, so that is second thing. Again, next, whether in this building there is a shear wall? No, we have not provided the shear wall. If the shear wall is there, then yes, shear wall to that particular shear wall nonlinearity is required to assign. Okay, so that is, but in this case shear wall is not provided, that also work is less. Then what is about the slab? Now the slab is not, we have we have modified is a rigid diaphragm, so the slab will not, is not going to fail, it is just moving in a horizontal x and y direction. Okay, so this is a complete non-linearity, complete non-linearity. So when you are confirmed that it is a complete non-linearity, then go for the analysis. Then whatever the hinges, just we'll check what are the different calculations it did. So just define section property and hinge property here. Okay, so the generated hinge, it shows these many hinges have been generated. Okay, just we click one, modify. It is a, it is this particular hinge is for column. Each and every element, different hinges are there. Okay, properties are different. Okay, for the column, it, the software has done this particular case. If we see this, all the calculations are there. Then see the interaction curve also. Automatically, since it is inbuilt, therefore all this. Otherwise, we have to define all this. Otherwise, all these values, therefore, and those hinges are called as a user defined. Since the elements are conventional type, so therefore we can use a auto hinge. Otherwise, if it is a composite sections are there, all these calculations are user are required to do the calculations. Okay. Okay, so now the hinges have been assigned. Then we'll go for the pushover analysis. So define the pushover load case. So for that, you go for a define a load case. Now here the pushover must come. So therefore, go for define, and here it is a push x. It is push x. Okay, push x. Then what is the type of this load case? It is static. It is static nonlinear. It is static nonlinear. Okay, static nonlinear is there. Okay, then while filling this particular table, start always from top to bottom. After this, then come here. Initial, asking what is the initial condition for the pushover. Initial condition is a gravity load case. First, the gravity should be complete, and then at the end of gravity, then pushover should start. Stiffness, so that it will take the stiffness from the at the end of the gravity load case. Okay, then here P delta effect. Okay, whether you want to perform P delta, if you don't want to perform this thing, none. If the regular P delta, click here. Software automatically account the P delta effect or P delta plus large displacements. Okay, whenever in the structure large deformations are there, just these are the just two options are there to solve the equilibrium equations. Okay, so more rigorous is this P delta plus a large displacement at every instant. At every instant, the stiffness matrix get updated and give the result. Okay, so this is most rigorous. Otherwise, more for a simple structure, go for a P delta analysis. Then yes, modal result. The software takes the result from the model. So modal analysis also is required. Then how to apply the lateral loads? We are performing the pushover. How to apply lateral loads? In this, there are three options: either a load pattern or acceleration generated lateral forces. Acceleration generated lateral forces can be applied, or a first mode shape. Whatever the first mode shape, in that case, it is this. So it is acceleration generated this thing. We go for acceleration generated. It is x direction, ux direction. This is always 1, or sometimes it is -1. I will show when it is -1. Just I will add this thing. Then go here. It is load application. Okay, what it is a, whether it is a load application is a full load or displacement control. Okay, displacement control. Load, whether we are monitoring the displacement. Our control is on a displacement. We are monitoring displacement at which node? This node. At software automatically suggested the point. Always this suggests the point at the top. Okay, and it is a 0.52. It is 4% of the height. It is 4% of the height. We can change this. Suppose we are performing a displacement based displacement what is called a displacement coefficient method. Then estimate target displacement. Estimate target displacement and push the structure up to that value. if you have user have the value, that is up to what level the structure give the value input here. Otherwise, the software automatically gives the 4%. Okay. Then in the first in the U1 direction, X direction, push over. Okay. Then go for a final review. Then we require the result. Software is asking whether, so what is the performance of the structure is that at the performance point, the structure is in the immediate occupancy state. Are you satisfied? Yes, immediate occupancy. So it is building is very safe. Design is very safe. So this information will get from the performance based design. Pushover analysis, then time history idea. That is all the gives the performance after the yielding. Performance after yielding. Suppose sometimes you will get the number of hinges here also. Okay, so that it shows the building has been collapsed. Then whatever the elements sizes we have provided, that is not sufficient. Then revise this thing. Revise the sizes and make the building as the make as a safe. Okay, so this is about the this thing. Then since there is a time is about only this thing 10 minutes, just I will show the next load case as a time history. So I will close the pushover. The next is next 10 minutes I will show how to perform the time history. Then define the function. First of all, define the time history function. Okay, so go here, and in the SAP library already ground motions are inbuilt. I think more than 20 records are there. So we can take the record from this. So from file, add function, then browse that particular. So it is time history function. Open this, all files. Okay. Now these are the records. Now by default I will take the first one, ground motion 1. Okay, so it is a open this. Okay, now what is, I will view this file. So this one. So this is the name of the earthquake, and this is the information about this particular earthquake. When this occur, how many points are this? Acceleration readings are there. All these are acceleration reading, and these are the near about 200 readings are there, and these readings are taken at the time step of 0.02 seconds, 0.2. And what is the this thing unit of this? Centimeter per second square. Okay, all this information are required for giving the input. Okay, so this is give the name to that thing. This is something, some name is like this, whatever the El Centro, Bhuj earthquake, what is the name of to the file list. Then okay, then header line to skip. What is the meaning of this? What is the informative level? How many are there? 1, 2, 3, 4 lines are there. Okay, 4 lines are there. So these lines are not required for the analysis. So that those lines are need to be this skip this. Then prefix means in between this a comma, then this full stop is there, like this colon is there. There is no prefix there. Then one line, how many readings are there? 8 readings. 1, 2, 3, 4, 5, 6, 7, 8 readings are there. Okay, so these are the 8 readings are there. 8 reading, and all the readings are taken at a regular interval of 0.02 seconds. Okay, and then display graph. These are readings. Readings have been taken at 0.02. One, two, three, four. 4 lines are skipped. No, there are no prefix. This is 0. This is 0. Number of points are 8. Display graph. Okay. Now this is the record. Okay, this is the ground motion. Is it? Now we define this. Okay. Okay. Then this is just function. Then define the load case. Define load case. Now here the time history should be there. Now we'll apply only in X direction because of the time constraint. So we'll apply time history in X direction. Time history in X direction. So it is a static. It is a time history analysis. Okay. So it is a time history non-linear and direct. Non-linear type and direct integration. Non-linear direct integration. Right. Okay. So this is again a continue from state of gravity. P delta analysis, yes, required P delta analysis. Okay. Then here Load pattern, it is acceleration type. In U1 direction, already they have defined this function. And scale, how much scale should be? Because these accelerations are there in centimeter per second square. And what is our scale of the model is meter. So therefore, all the readings are required to convert from centimeter to meter. So it is 1 divided by 100. So that is 0.01. Correct? 0.01, add this. Okay, 0.01. Then number of output time step. How many are there? Number of output time step. How many are there? 2000 readings are there. Okay, so these are 2000 and output time step is 0.02. All the readings are in the interval of 0.02. Okay, now here proportional damping. We are performing a nonlinear time strength analysis. Damping is going to change. What is called as a proportional damping. So that is now here. Now there are give the information or damping specify by period and specify by frequency. I will specify by period. Specify by period. So here in x direction and y direction, you just give the input. Now we have noted this in this. So in x direction, time period for the first mode is 1.07, and second time period is 0.32. These are the two time periods in x direction in successive translation mode. And constant damping 0.05, and this is also 0.05. Then recalculate. Now we calculate the parameters. Mass proportion coefficient. Then here, these are the, by default, these are the some methods are there to solve the integrations. So Hilbert-Taylor method is there, which is a next version to Newmark method. Newmark have developed this method in 1948. Then this is 1980, modified and added one alpha. Madam, shall I continue for next 10 minutes maximum? Okay, now it will take more time because number of hinges are there. So therefore, I will cancel this analysis. I'll cancel this analysis, and it gives the result. Then afterward, from the table values, and you can calculate the drift and all this. Okay, so therefore, so in the case of this thing, only thing is that in the case of incremental dynamic analysis, only you require to make a changes here. That is assign, define load case. We have defined the load case now as a time history analysis. Load case is there, modified here. So this is the this is to convert this scale factor is to convert from centimeter to meter. Okay. Now here, suppose you want to perform the first analysis for 10% amplitude. So once again multiply this value to 0.1. 10% means 0.1. Run the analysis, get the maximum drift value. Okay, yes, maximum drift value, that is for 0.1 G. Okay, next is change to 0.2, multiply by 0.2, run the analysis 0.3, 0.4, 0.5, unless your global drift reaches to infinity. Then stop the incrementing. Then go for next, go take the next ground motion. In this way, this is for first ground motion. Okay, in this way it is to be performed. Madam, shall I continue for 5 minutes next? Yes. Okay. Only in the last session, condenser session, some difficulties were there. That I will this thing. First is that I want to show to this model. I want to show this model that how to assign the springs. Okay, first thing is that whenever to study the soil and structure interaction, then it is necessary to replace this rigid support by a spring model. Okay, then the command is that whatever this these supports are there, first of all remove and calculate the stiffnesses in x direction, y direction, and rotational stiffness, and give the input. Time being, I will substitute the values at 100 like this. Some values, rotation stiffness, then okay. These are the springs. Now this is a linear interaction, soil structure interaction, but linear behavior. Suppose you want to study the nonlinear behavior, soil structure interaction, then I think instead of SAP, you go for SAFE. That is also CSI product, and SAFE is only for foundation. So in that, the nonlinear behavior, this is the linear behavior. If it is there, then this particular approach, that is spring model, it is Winkler model, is more than sufficient. Okay, that is about the how to assign the spring. Then how to assign the shear walls. Okay, one thing is that. Then for that, go for XZ plane. Already I have defined the shear wall. Okay, already I have defined the shear wall. Therefore, I have defined the shear wall. Then go for here. Then this is the shear wall is there. Okay, then this is the shear wall. See, the shear wall has been assigned. Okay, how to give the non-linearity to the shear wall? This, whatever the shear walls, these shear walls have been assigned. So we can see like this also. Okay, now these are the shear wall. Now how to give the non-linearity to the shear wall? What is the command here? So the shear wall non-linearity can be assigned by two ways, either by using a wide column approach, or it is a multi-layer. That is a beauty in what is a good facility in the SAP 2000. So that is a define. Then go for a it is in the define section property area section. Now here, whatever the shear wall is there, modify this. Now this is modeled as a shell thin. Instead of that, go for shell layered nonlinear. Shell layered nonlinear. Modify this. Okay. Now here again modify this quick set. Okay. Now here give the input. What is the thickness of the wall? What is the reinforcement grade is there? What is the thickness? Whether the reinforcement is to be provided 1 layer, 2 layer. Okay. Then the non-linearity in which direction? So we are interested in only 2. We are not interested in one vertical direction, and this is out of plane non-linearity, that is also not required. So only 2 direction. Then here the bar whatever are there provided in the shear wall, that means shear wall design must be ready. What is the bar diameter, spacing, everything it is required. Then it generates the layers, and the SAP automatically gives the non-linearity to each layer. Okay, so that is, in this way, this is a very good and correct approach, and this is a distributed approach. Okay, distributed this thing approach. Then section designer one is there. Section designer, whenever there is a non-conventional section, like a composite section is there, or it is a retrofitted section, then how to deal with? So it is a section designer, frame section. Here, go for add new section, go for others, and here it is section design. Column, concrete column, section designer. So here we can create any section. Okay, and we can, this is a section is there. Then whether it is a reinforcing section is there. Yes, it is reinforcing. Yes, it shows the reinforcement. So here we can create, so this is a command, this is a special tool is there. Here we can build a non-conventional composite section, retrofitted sections are there. FRP in previous session, one of the question was there, whether we can, the FRP this thing material has been used for the strengthening purpose. Then come here in this particular, that is user need not necessarily to, in the same case for the time history analysis also, once we define the function and define the load case, automatically it one by one. all of a sudden it is not. So these are the inbuilt load cases. How to create artificial time history for artificial earthquake. Okay. For we required what? We required a record. Record in the sense acceleration. So that is the researchers. This thing is there. The work is there. That is how to create. That means create a table. This thing is there. Shake table is there. Shake table is there. And if your instrumentation is there, then instrumentation is there, then by using that instrumentation you just create the this thing acceleration readings. But actually the question is that when it is required to go for artificial time, if the natural records are not sufficient, natural records are not sufficient in the sense the natural records are not giving the response as you require, okay, then in that case go for synthetic. Okay, then what kind of response you expect, so that record actually must be available with you. Okay, so therefore that is then if it is available, then we can perform this thing analysis. Okay, next is which is the best analysis analytical model to verify the hysteresis behavior performance. What are the standard values of energy dissipation? Okay, what is the best analytical model to verify the hysteresis? Okay, now there are different models are there. Okay, that is first is stiffness degradation model is there, pinching behavior model is there, and then the what is this thing Takeda model is a stiffness degradation model is there. Okay, strength degradation model is there. It all depends on the what kind of material it is. If as far as the building is concerned subjected to seismic, then many researchers have preferred that go for the Takeda model, which is a stiffness degradation model, because we are most in the case of seismic analysis, we are more interested about the stiffness degradation. So go for stiffness degradation. For other, suppose the wind analysis and nonlinear is there, then maybe the other type of model is, but all depends on what type of the material is there. If it is a masonry building is there, then I think instead of using a Takeda model, other model. But I don't know much more about this. I know only about the RC buildings. Next question is that no. Question is that Indian earthquake data is not available on peer ground motion database. Yes, it is not available. Somebody has questioned this. Prashant have answered this. Because peer Pacific earthquake ground motion is only for in the California region. Earthquake, the Indian earthquake data you will get in the Indian research centers only. It is Madam Padnis Madam also given the answer of this. It is available in IIT Kanpur database. Okay. Is torsion allowed in second mode? Torsion allowed in the second mode. Our Indian standard code says that the building design should be new. If it is a new building, is that our design should be such that in the first mode torsion should not be there, because the first mode is such that mass participation is higher. Then second mode, whether torsion is allowed, it depends on mass participation. If the mass participation is very less, then it is allowed. It is allowed. But actually, if actually we cannot control on the second mode. We have the control on the first mode, because mass participation is more in the first mode. Second and third mode is not that much significant compared to the first mode. So therefore, if it is there in the second mode, will it be okay? It is okay. How to choose between ATC 14, FEMA 356 hinges? ATC 40 hinge property are not there in ATC 40. ATC 40 is only capacity spectrum method. Capacity spectrum method is described in that, and FEMA 356 is there. FEMA 356 is there. There the hinge properties are given. FEMA 356 is there. Then this thing ASC 41 is there. In that these particular tables are. But all these are American this thing. You will find the same properties. If you see the FEMA 356 hinge properties and ATC this thing, ASC 41, you will find the same properties. Only just like our previous IS code and the new IS code, a minor changes are there. Okay, to some values are there. Otherwise, all values are same. Similarly, here also the hinge property are not significantly changes. Minor change may be there, but that may not be in the hinge. Somewhere in other clauses, there are changes. Yes. Is it possible to model diagonal compression only member for infill? Yes. Yes, yes, yes. That comes in the infill modeling. That's why I'm saying that whether the infill contribution are considering or not considering. In our case, whatever the building we have considered, in that case, contribution of the infill to resist lateral load have not been considered. Okay, right? Okay, so that is now consider the contribution of the infill is actually what required to do here. In this case, only the weight of the masonry we have applied on a beam, right? Infill contribution to be considered means actually here the infill is required to model as a diagonal strut. Okay, just like a column. Now diagonal strut means it has a dimension. Thickness equals to thickness of the beam, whatever the wall thickness, and width is there. Okay, width is there. And to calculate the width in recent IS code, whatever IS 1893 is there, and 1893 or 13920, in that, and many developing countries, ATC 40 and this thing, FEMA, everywhere it is, the equation is given to calculate the width of equivalent dies. Then after calculating the size of the infill, then assign that particular. Then in the frame, you'll find the diagonal member, which represents the infill, and give the property, infill property, brick masonry property to that. Just like a concrete for the concrete column beam, we have assigned the property of the concrete and the beam, concrete property. Similarly, for this also, Young's modulus value, Poisson's ratio value, all the property should be given. And then regarding the nonlinearity, okay, then next point is that after only assigning the member is not sufficient. To assign the nonlinearity, how that particular element will going to fail, it will fail in the axial compression. So therefore, we must have, there must be a data regarding the stress and strain behavior of the what is the masonry column. Okay, so that data is required to give as an input. So here it is required to create a hinge, develop a hinge. Okay, what is called an axial hinge. Okay, so actually because of the time constraint, there is a limitation. Otherwise, it is very simple to assign that particular hinge. And then after defining the hinge, then we can assign this. Is it possible to model diagonal compression only members for infill in the thing? Yes. Any other question, madam?
Okay, so we have completed the session and Sir has answered all the questions. So now we are going to finish this particular meeting. I would like to thank all the participants for attending the session. The attendance sheet is shared over Google Meet. I'll share the feedback form for Dr. V.S. Patil on the Telegram group. And the next session we will begin around 1 to 1:15. Thank you all for attending this session.